Hey, what up, and welcome back to lesson 2.6. And we are jump starting here with this diagram, which should look familiar because that's where 2.1 started. And in 2.1, we were given the information that points M and N are at the center of their respective circles. And we were trying to figure out things that we know are congruent. And basically, all we were able to get was the radiuses, the radii, things that go from the center of one of the circles, this circle too. CB and AB, though, weren't radiuses, weren't radii, so we weren't actually able to conclude anything about them. But now, they want us to conclude if they are congruent. Do we have the tools? Well, we could claim that they are congruent if they were corresponding parts of two congruent triangles. If they matched up with each other, and if we knew the triangles they were part of had to match, had to be congruent, and that they were the same part of those two triangles, and the triangles were the same, then we could say, yeah, they're definitely the same. And we can do that now. We have the skills. And we might be tempted to try to do these right-looking triangles and get them to be congruent. However, we don't have enough information to do that. We know there's a shared side here, and we know there's a radius here. So that's two sides, but we don't have any angles. And we don't know what this is, if that's what we're trying to get to. We don't know this is a right angle. It looks like it is, but it doesn't have to be based on the diagram, based on the fact that we're given that there's two circles, and that's all we know. The other thing you can trust from diagrams is that straight lines are straight, and lines that cross do cross. So we know these lines cross. We don't know where, how, or what's going on. So this could be at an angle. They cross here. This line is straight and this line is straight, but we don't know about the angles. All right, so let's work our way there using the fact that segment CN. Okay, full disclosure, I've made this video 3 times today. I keep messing it up. Or after 20 minutes of a perfect video, my computer unplugged. And so I'm just going to pull up what I made before. Okay, so these are the same. These little ones in here, CM and AM, are the same. And we have a shared side here in the middle, MN. So we're not doing the right-looking triangles. We're doing the chevron-looking triangle, the arrow-looking one. The pair of arrow-looking ones. Because we have side, side, side. That middle side is reflexive. It has a shared side. So then we can confidently say that those two arrow triangles are the same side, side, side. But if they're the same, then these angles are congruent by CP/CTC. And because those angles are along a straight line, their pairs have to be the same because all lines at the line adds up to 180 on the top and the bottom. And once you take away these two congruent triangles, congruent angles, you're left over with the same pieces. So those angles are the same. Then we have a teeny little tiny shared side in here. So now we have side angle side. So we can say that these right-looking triangles, these little bitty triangles, which are triangle CMB and AMB, they're congruent by SAS. Therefore, finally, the thing we're trying to prove, segment AB and segment CB, where's the A? A, B, zoom out just a little bit. A, B, C, B, segments are congruent by CP/CTC, which is the second time we've used that in our little proof here, because those are corresponding parts of two congruent triangles. They're the same side. Okay. Got to move on. Running out of time. It's been one heck of a day. So we're going to justify our construction strategies. Yeah, we've been constructing stuff, but how do we know that we've really been constructing stuff? I mean, how do we know that the things that we've been making are those things? So compass, straight edge, compass and straight edge constructions can be justified using tools such as definitions and properties of rigid transformations, identifications of corresponding parts of congruent triangles, and conjectures about the attributes of sides, angles, and diagonals of special types of quadrilaterals. So, study the steps of the following procedure for constructing an angle bisector and complete the illustration based on the description of the steps. So, using a compass, draw an arc. Here, they already did that part. That step's done. That intersects each ray of the angle to be bisected with the center of the arc located at the vertex of that angle without changing the span of the compass. Now, usually for angle bisection, you can change the span of the compass after you make this first arc. And in fact, for obtuse angles, you must make it bigger or you won't be able to copy an obtuse or bisect an obtuse angle. But they don't want us to because they want us to make a rhombus. You may have been noticing, because the next one is, without changing the span of the compass, draw two arcs on the interior of the angle with the center of the arcs located at the 2 points where the first arc crossed the rays. And then, with a straight edge, draw the ray from the vertex to the place where those two crossed. So this is standard angle bisector. Well, not totally standard because they wanted us to use the same size arcs because we also just made a rhombus. So let's make that because we're going to use the rhombus logic. What is rhombus logic? Rhombus logic is that all of the sides are the same. And not only that, we have a shared side here. So by the reflexive property, this side. So now we have two triangles. This guy and this guy back to back with three sides all the same. So by side, 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 these triangles are congruent. So then, by CP/CTC, their corresponding angles here are congruent. And if these corresponding angles are congruent, then this is definitely a bisector. It bisects that angle. So we've just justified the construction of an angle bisector. We've proved that when we do the construction of an angle bisector, we are in fact making an angle bisector based on rhombus logic, triangle congruence, and corresponding parts. Let's see how I wrote it earlier. This construction creates two congruent triangles that have corresponding angles at the OG angle, the original angle, that we were trying to bisect. Because it makes two congruent triangles there, it has split the angle equally. That's the definition of an angle bisector. So lots of times proofs will end with definition of a bisector, or definition of that, or definition of this. What you should be thinking of is that's the definition of the thing. We're trying to prove a thing. We've proven the definition of the thing. Therefore, we proved the thing. All right. You can pause and write that down. The next one is number 2. Study the steps of the following procedures for constructing a line perpendicular to a given line through a given point and complete the illustration based on the description of the steps. It's been one heck of a stressful day, I gotta tell you. 10-minute break's gonna start pretty soon. I'm just gonna let them hang out in the hall because I gotta get this video done. Draw an arc, we did that. At the 2 points. Without changing the span of the compass, locate a second point on the other side of the given line by drawing two arcs on the same side of the line with the center of the arcs located at the 2 points where the first arc intersected. Okay, so we're kind of making a perpendicular bisector, but it started with this point and they reached out and found 2 points equally distant away. Now we're reaching back. They only actually want us to make the one on the bottom, but yeah, not too accurate. They're asking us to prove why is this line really perpendicular? Are we so sure? We think this is perpendicular, and by construction it is, but how can we prove the construction makes a perpendicular line? Yes, using rhombus logic. Because all of these lines, wait, that's not where it was. Oh man. all of these lines. Why do I have to? We centered these two circle arcs on these 2 points. So that's where the radii go. The first 2 lines I drew were not radii. So I don't know how long they are. I don't know how long these are. They're not they may or may not be the same. But I definitely know these 4 are all the same. Rhombus logic. So, along with the same as last time, this shared side, this is the one we just did, means that this triangle and this one are congruent, which means their angles are congruent. Okay? But now, I'm going to cut this off here and say that because of this shared side, I now have side, angle, side, side, angle, side. So I know these 2 mini guys are congruent, which then by CPCTC, I know that these 2 angles, these corresponding angles, are congruent. Now I don't know their right angles yet, but I know they're the same. Let's call them x. X degrees. They're along a straight line, and we know that straight lines contain 180 degrees. So x degrees plus x degrees equals 180 degrees, has to. Straight lines are 180 degrees because they cut a circle in half, right? Full circle is 360, cut it in half, it must be 180 there. So now 2x equals 180. Now divide by 2. And algebra to the rescue. You're right, x plus x is 2x. Okay, so now algebra. Jumping around here. Sorry, guys. Super stressful day. And I'm in a hurry. All the stresses. So these are actually 90, and if they're actually 90, that is actually perpendicular. So constructing a perpendicular line, we proved why. Using radii of circles, using rhombus logic, using CPCTC, and triangle congruent. We've proven that is a perpendicular line. Let's see what I wrote earlier the first time I filmed this. We made a big rhombus, which gave us some congruent triangles along a straight line with corresponding parts, the angles, on that straight line. So those angles are 90. Because I have to add up to 180. Pause and reflect. Study the next one, last one. Study the steps of the following procedure for constructing a line parallel to a given line. So we're going to do through a given point and complete the illustration based on the description of the steps. Okay, so this starts with just this line and this dot. Then, using a straight edge, draw a line through the given point to form an arbitrary angle with the given line. An arbitrary angle just means some random angle. Doesn't matter what the angle is. So they just chose one and drew it. Because no matter what the angle is, when you copy it, you will create a parallel line. Using a compass, draw an arc, a portion of a circle, that intersects both rays of the angle formed. So they did this, with the center of the arc located where the 2 lines cross. That was their second thing. Now, without changing the compass, of course, move to make a second arc up here that crosses the ray. The second arc should be as long or longer than the first arc. So, because we got to make sure that we hit this point out here. Set the span of the compass to match the distance between the 2 points where the first arc crosses the 2 lines. Without changing the span of the compass, draw a third arc that intersects the second arc. So in other words, they're saying measure this distance here. I'm going to do it from the top side. And don't forget to make this line here, make this arc, sorry. It shows me you measured it. And then come over here. Aha, something is wrong. I'm going from the wrong spot. Aha, something is right. There, because I measured that from where the arc crosses this ray, I got to slide all the way up to where the arc crosses this ray. I don't know why I stopped at the dot. I guess I'm really stressed. It's 10-minute break right now. Students are wondering why they can't get in here. And lastly, with a straight edge, draw a line to the given point and the point where the 2 arcs intersect. So this is the given point that we started with, and there's where the 2 arcs intersect, and that is parallel to that. Now, why are we for sure that that's parallel to that? Well, because this and this and this and this are all congruent because they were made by the same circle, the same radii. Furthermore, this distance here is a different radii that we made, that we measured, and we put that same radii right here. I guess this is singular radius. And so this little thing is equal to that. So now these are congruent by side, side, side. and these are corresponding angles right here and here. And if those are corresponding angles, then these are parallel lines. That part's a little hand wavy, but we've been graphing, we've been graphing parallel lines with the same slope, and they always make the same angle with the y-axis, so we can kind of maybe accept that if it makes the same angle with the same line, they must be parallel with the same slope. So let's explain in detail. Two of the sides of each triangle we made are radii of congruent circles. Likewise, the distance across those arcs, so in other words, this distance, are congruent to each other. That's side, side, side for the two triangles. So by CPCTC, by corresponding parts of congruent triangles are congruent, the angles formed with the two lines are congruent. So they're parallel, and you can see right earlier today when I went smash, smash, and then kicked my power strip and turned off my computer and ruined that video. And this video is 2 minutes shorter, so that's a win. All right, I'll see you on Monday.